from Northeastern University, United States. So her research interests include power electronics and power systems. Recently, she has worked on a practical design of current mode boost converter by using LM5022. It includes average mode, startup, and low transient simulation by TI, TINA, and LT Spice. So she has developed schematics and PCB layouts by using Altium Designer 21. Includes various test setups, and she has worked on various load transient tests, startup and shutdown test, DCM, and continuous conduction mode tests. So on behalf of IEEE Vizag based section, and on behalf of IEEE Power and Energy Society, Power Electronics Society, and Industrial Applications Society, so we warmly welcome you for today's expert talk on a practical design of boost converter, current mode boost converter by using LM5022. We are very thankful for accepting our invitation to give the lecture. Now I request Lakshmi Narayana sir to give some opening remarks about our Vizag Bay section. Sir?
Yeah, Dr. Zhang and Dr. Ashwin, I think I need to give little 1 minute introduction about our section. Our section has basically started in 2020. The very youngest section in the world, I can say. Yet we bagged the highest award in our region. Under small section category, we received the highest amount for the best performance for last year. That is exactly a greatness, and not to me, to all the volunteers of Vizag Bay section. We are really conducting a very excellent programs, and really I'm happy that Zhang has agreed to deliver such a talk. I don't want to take much time on that. I request Zhang to go ahead to present her talk, and in fact to tell the youngsters how to start the research at the early stage of their work. Thank you very much, and over to Zhang.
Thanks. Thank you so much.
Thank you. Well, you can start, madam.
Okay, sure. Okay, so first of all, I should say I was so excited and honored to be invited to be here and make the expert lecture about the practical design of the current mode booster converter. Yeah, my name is Qinyu Zhang, and my project mentor, his name is Ye Zhao. And let me briefly introduce myself. I got my master's degree from Northeastern at December 2020, and my concentration is power electronics. And I got my co-op position at Analogic Corporation in the MRI group. The position is MRI hardware intern. And I will start my full-time job at Infineon Technologies as a senior firmware development engineer. And also, I want to thank my project mentor, Ye Zhao. And I also want to briefly introduce him here. He got his master and PhD degrees from Northeastern, also with the same major with me. And he's right now is a principal and electrical engineer at Analogical Corporation. We're in the same team. In his group when I was the intern at Analogic. And he's also a part-time instructor on Udemy. He has two famous courses. The first one is the LT Spice tutorial for beginners, and the second one is automate LT Spice circuit simulation using Python scripting. If you are interested about him, you can find him on LinkedIn or you can search him on Udemy. So today our topic is about the practical design of a LM5022 booster converter, which uses a peak current mode controller. So let me briefly say the specs of this booster converter. The input voltage is from 6 volts to 48 volts, and the output voltage is stable at 50 volts. And the output power is 5 watts, and the maximum efficiency will reach 90%. And the switching frequency would be 400 kilohertz. In case that some of you are not familiar with the boost converter, I have prepared this topology and two working status. You can say on the left is the topology of a basic boost converter. It's included a power supply, inductors, diodes, switch, and output capacitors and the load. So on the right side, the top right is the on state of the boost converter. So it's when the switch is closed, current flows through the inductor in the clockwise direction, and the inductor stores some energy by generating a magnetic field. Polarity of the left side of the inductor is positive, which means the left side of the inductor is positive. And for the bottom right, which is the offset state of the booster converter. So when the switch is opened, the current will be reduced as the impedance is higher. The magnetic field previously created by the will be reduced in energy to maintain the current towards to the load. So the polarity will be reversed, which means the left side of the inductor will be negative right now. As a result, two sources will be in series, causing a higher voltage to charge the capacitor through the diode D. So that's a brief introduction about the boost converter. Okay, let us see the comments of this design review. So first part would be the LM5022 boost converter simulation, which will include the MATLAB and the LT-SPICE simulation, and also the TINA simulation is from Texas Instruments. And the second part would be the PCB design and the part selection. So it will be include a PCB schematic and PCB layout I completed by Ultimate Designer, and selected part parameters on DigiKey, Texas Instrument, and also choreographed. The third part would be the bench soldering, and the last part would be the bench test. It will include several test results and several test equipment I used. So let's go. The first part is the boost converter simulation. Well, for the start of the design, we should use several simulation software to make sure that our design idea is correct, or to make sure that it can work correctly. Well, for the LM5022 controller, it has a small signal analysis over control signal. We can see inside the LM5022, it has a small signal circuit over here. The 5 volts and can you see my mouse here? It's this part. So we should consider it we should include it in our transfer function. So this part is really important because the data sheets do not include this part, but we should consider about it. And then we could see the transfer function of the power stage in a current mode boost converter. I should clarify that the current mode boost converter has different transfer function with the voltage mode boost converter. So that's why I want to show here. It's a current mode boost converter. So the transfer function will be like this. And the second part is the transfer function of the type 2 controller. So for a type 2 controller, the type 2 compensation has 2 poles and 1 0. And the 0 is placed somewhere between the poles. So power stage function, also called the control to output transfer function. And then we got the total transfer function by timestamp, and also with the 1/3 here, as we just mentioned. So this is the power stage body plot calculation by MATLAB. We could use MATLAB to do some basic calculation for us. As you can see, we could see the ESR0 from the power stage transfer function, and also the pole from the power stage transfer function. And I put the 1/3 in the power stage, so you can now see it on the behind pages. So this 1/3 is over here. And here's the result for the power stage simulation on MATLAB. We can say I choose the crossover frequency equals to 5 kilohertz. So at 5 kilohertz, we could say the magnitude would be -8.05. This is important because we will use this to design our controller. And here's a reference I quoted from TILM5022 Evaluation Board User's Guide. We could see the relationship between the phase margin and between the phase margin and the load transient. I mean, why the phase margin is really important for the whole system, because the phase margin, if you have enough phase margin, your system will be more stable. Like the first picture, the appearance is what is known as the critically damped, which means it extinguishes very cleanly in only one single complete ring. So this is ideal performance because it gives the fastest possible settling time and very good stability. It only have like one single ring and then it come to the stable. And for the second one, the settling characteristics now show a bit more ringing after the transient occurred. The transient is like over here, and it has more ringing than the first picture. So it can be seen that even though the phase margin is only 30 degrees, the settling is fairly clean and probably acceptable for most applicants. But for the when the phase margin goes to 17 degrees and even the 5 degrees, it can be said that the raining is beginning to take on the appearance of the sine wave oscillation, becoming even more obvious as the phase margin is reduced to only 5 degrees. So it means that the raining, you could say the raining becomes obviously when the phase margin only have the 5 degrees. So also the use the MATLAB for our type 2 controller calculation. Here's the crossover frequency and the 0 for the type 2 controller. The pole is equals to the geometric mean of the, sorry, the 0 equals to the geometric mean of the, I'm sorry, I'm a little nervous. So the crossover frequency equals to the geometric mean of the 0 and the pole. And we could use that function to calculate the pole by have already decided choose the crossover frequency and the 0. So we could calculate our type 2 controller by these functions, and we could get the result of the resistor and capacitors values, and we could put them in our TINA TI simulation and also the Aptiv SPICE simulation. So here's the combined results of the power stage controller and also the total loop. we could say at the crossover frequency, this is a power stage magnitude, which is equals to minus 8.09. Yeah, just we mentioned. And the total loop gain, at the crossover frequency, the magnitude should be the 0. So that means our controller works well in MATLAB simulation. And our phase margin here is equals to 68. So which means our our system is stable, have enough capacities to deal with the low transient. And here's the simulation from LT-SPICE. Here's the only type 2 controller from here. We could say that this body plot is a standard type 2 controller body plot. It has a the phase margin, the phase boost would be reach its maximum value at the crossover frequency. Okay, we're going to start our TI-TINA simulation. The first part is the body plot simulation, which we could get the power stage body plot by it's equal to could be expressed as V out divided by V com. I added a test point here, which is the comping voltage, and we could use the output voltage divided by V comping voltage, so we could get the body plot of the power stage. And for type 2 controller, it's equals to pumping voltage divided by V1, which is over here. And for the total loop body plot, it equals to V out divided by V1. So yeah, we could say that it's more close to the realistic than the MATLAB simulation. So you could download this simulation package from TINA's Texas Instruments website. It depends on your controller you choose. I choose LM5022, so you could search it on the TI official website, and you could get the simulation package. And the second one is the startup simulation. You could say I input all the controller values, all the values from the controller we just like calculated in MATLAB, and then that's the whole system will be like the how we design, so that all values equals to the design value, the design results from the MATLAB. And here's the results of the start simulation. You could also see in the tester results in the last part of this PowerPoint. I zoom this part of the results. So it will be look like this. And the last part is a low transient simulation for the LM5022. And we want to say like when the whole system becomes too stable, we want to say how's the when we add and low transient here, if the stable could be back to the stable, could be back to the stable or not. So we do the simulation, and we could say the undershoot of the low transient is 290 millivolts. So it's really small, and that could mean our system could become stable really quick. And the overshoot is also the 290 millivolts. Okay, so the second part is the most important part I want to explain. I want to show here. It's a PCB design and the part selection. It will be included how I complete my schematic and PCB layout by Ultimate Designer. So this is an essential part of the boost converter. The BOM of LM5022 booster converter is an essential BOM, not the all of. Okay, so that's just the essential part. So the power stage, we could see the inductor's value here and also the single external resistor, which will influence the, like it depends on our switching frequency. Like you choose different value of the single external resistor, it will be like you will get the different switching frequency of your design. So that means if you want to choose different level of your frequency switching, different switching frequency of your controller, you could just change this value so you could get what you want. And also the output capacitor, and we assume that the equivalent series resistance, which is ESR of Cout, is 100 milliohms. And the current sensing part, and also the type 2 part. You can see the 0 pole crossover frequency and the feedback resistor, the type 2 controller value, the capacitors and the resistors here. So let me clarify here why this 3B threshold. You can see on my board that it will be easy to change value if you want to justify your type 2 controller when you are testing. So here's the output and input capacitor I choose for my booster converter. And for the power inductor, I calculated in the MATLAB. For here, we should make sure that we have to choose the maximum value here to satisfy all duty cycles, or say all circumstances. So I choose, you could say the first one. The value is the 180. And why I choose, I have 3 choices. Why I choose the first one? Because of the DCR of the inductors is smaller than others. And smaller DCR means it will have like smaller influence of our main circuit. So that's also an important part when you are choosing an inductor. So here's the inductor look like. Power diode selection from DJ key, you should consider the voltage derating. We assume that the derating of the output voltage is 80%. So that means the voltage tolerance of the diode should be at least larger than 50 volts divided by 0.8, which equals to 62.5 volts. And for power diode, you could say like all parameters on DJ key. It has the size, the package, and the supplier devices package, and also the voltage and the current, and all of the parameters. It is really clear on the DJ key. When you do the part selection, you should consider the price, you should know that when you work for a company, you should make sure that you could make the budget as low as possible. Not every circumstance. I just to say, yeah, maybe your employer want to you just minimize, like reduce the budget to make the same goal. So that's also important. For power MOSFET, I choose this one, and it's an N channel 2.7 amps and 1.5 watts surface mount. The package is 8SOIC. And for the power MOSFET, you should consider the losses of the MOSFET. Like for MOSFET, it should be include like 3 important part of losses. The first one would be the conduction loss. And the second part would be the gate charging loss. And the last part would be the switching loss. And the total loss will be like plus them together. And you should know that for like low output power, the losses is really important when you are choosing power MOSFET. Because you don't want your MOSFET to have much influence on your circuit. So you should make sure that the power losses is not very high and not occupy like most percentage of your output power. It means you will not lose that much energy through the MOSFET. And another important part is the under voltage lockout protection. We could say here when the input voltage equals 48 volts, the voltage on the under voltage lockout pin is well over 7 volts. According to 6.1 from LM5022 datasheet, the absolute maximum ratings, it shouldn't be over than 7 volts, or it will cause the permanent damage to the devices. So we could say here when the input voltage equals to 48 volts, the under voltage lockout pin voltage will equals to 9.92 volts, which will like much more bigger than the 7 volts. So it will be damage our circuit. So we should make sure that we have a over voltage protection here. The Zener diodes are mostly the first choice to protect the circuit from an over voltage condition. The Zener diodes I choose for the under voltage lockout over voltage protection. And I put a website here. It's like a tutorial to tell you how to design a simple over voltage protection circuit using Zener diodes. I calculate the biasing current, and the total current will be the hysteresis current plus biasing current, and the power rating you could calculate by the it's total current times the voltage of the Zener diode, and from the you could also calculate the temperature rise from because you have already have the power through the Zener diode. So for the temperature, if you don't have the instruments to measure the temperature, you can roughly feel the temperature by your hand. The general hand temperature tolerance is about 60 degrees Celsius. So it will be means if you can put your hands on the components you want to see the temperature. If you can, if your hands is okay with that temperature, it means it wouldn't be over 60 degrees Celsius. And I also calculate the temperature rise of the RSNS. I can find the you can find the thermal resistance for different package here. So for here, the RSNS is the package of the RSNS is 11206. So I use the functions to calculate its like temperature rise here, which is equals to 24.46 degrees Celsius. And this is a variable resistor. So the underscore CHA is the input signal monitoring point for body plot analyzer, and underscore CHB is the output signal monitoring point for body plot analyzer. Here's the body plot my mentor sent to me. Because I didn't have the equipment to test the body plot, but he did. So he tested and sent it to me to say this is the power stage body plot, which we can see is the test. This is the simulation. This is the test result, and as we mentioned, the simulation result from MATLAB. We could say that these two results are consistent. Okay, the software I used to complete my PCB layout is called the Ultimate Designer. I used the 21 version. So the Ultimate Designer is it's very powerful software for PCB design. And absolutely, because it's powerful, so it's also expensive. You could say that it's cost $325 per month. But don't worry about it. If you are a student, you could get a free 6-month trial with your valid student email. And this is the interface you could see on their official website. You could register with your name and your address, and also the university's name and your valid student email. So you could get a free 6-month trial. And the tutorial I recommend you could easily find a lot of tutorials on YouTube, but I recommend Robert Ferinance's beginner series. He's a very patient and detailed person. He said everything in details, and the example he used in the beginners series is very simple. And you could learn like how to use the Ultimate Designer by it only have 5 videos in that beginner series. So you could learn that very quick, and you could understand and hands-on really quick by this video tutorial. I hope it can help you, because I have watched this whole videos like several times. Every time I think about like which details I forgot to use, which tools I forgot, I will rewatch it and like review it to find which tools I could use or how to use the tool. Okay, maybe I could display how to like the interface of the Ultimate Designer. Sure. Can you see my screen right now? It's the Ultimate Designer interface.
I can say it.
Thanks. So for this is the schematic I completed with the Ultimate Designer. I can show you later. So for here is the PCB library. You could, it's a really like you can say here's like different package. This is the 0603 package of the capacitors, and you could put, you could name your package and also put some description here and the type, the height. You could like build it by your own, like build by your own requirement, or you could find the reference on the DJ key and also Texas Instrument official website, and you could draw your, you could build your PCB library by your own. Or you could download it from the website. It has several PCB I have here. You could say that have different layers. You can define like which layers you want to show. The basic one is the top layer, the assembly top and the assembly bottom. Sorry, no, it's, yeah, it's the top layer and the bottom layer here. One, yeah, the top layer will display as the red color. And for the purple one is the mechanical layer, I think. I didn't remember clearly, but you could find out like how to draw a PCB, draw the PCB library from the Robert's video. And this is the schematic library. You could build your like libraries with the like the several different capacitors. And you can see here's the 3D model here. And I will show you how the 3D model will be the best thing in this software later. And this is a socket. I can see like so many different components you could draw by your own with the standards you want to obey. And for the it has also could set up with different like different distance you want between the lines or the through hole size, and all of this you could design by yourself. Yeah, it has so much like characteristics you could design by yourself. It's a very powerful software. I maybe make you confused here, but I want to show you like how powerful it is and how like how many customer you could customize by yourself with your standards you want. And here's the schematic of my booster converter. So as we just mentioned, the Vin will has the range from 6 volts to 48 volts, and the input is on the left and the output is on the right. So you can say the input capacitors over here, the C in 1 and C in 2, and 2 bypass capacitors, and the output voltage, under voltage lockout overload protection, the Zener diode over here, and the power inductor, and the diodes, and the output capacitors, and also LED, small LED here to indicate that your circuit is working or not. And the type 2 controller is over here. You can see the COM pin and the feedback pin connect together, and this part is the type 2 controller. And this part is power MOSFET. I added a female socket here for the type 2 controller. You see directly more clear on the PCB part. A female socket is over here. It is connect to the type 2 controller. As I said, you could use the through-hole components to easily change the values of your type 2 controller if you find out that the values of the controller your design is not match your power stage in the realistic. Because sometimes simulation could work well with all the values you design, but for the real part, it could not be exactly the same. So you should justice your values and match your power stage, make the whole system stable. Okay, let us back to our display here. Sure. So you can say, yeah, it's the schematic. I just show. And I add several test points here, thus with different colors. You can figure out on your board at once. If you want to test your switching point, here's the switching point test. The test point of the switching point is the yellow color. The input, output, feedback, and comping is all red. It's all red here, but I remember it's like have several different colors on the real board. So for the PCB layout design, the really important part is to figure out your high slew rate loop. So like different converter have different topology. For the booster converter topology, I show you at the first several page of the PowerPoint. Maybe you also remember that. So for the booster converter current loop, it has two parts. The most important thing we should consider is to keep the high slew rate current loops as tight as possible. Depends on different topologies. So of different converters, their high slew rate current loops are different. So we can say here for the booster converter, the light gray here, the bigger loop. The light gray, the outer loop represents the high current path during the off time. Remember the offset state of the booster converter. So this is the high slew rate when the switch is off. And for the dark gray, the inner loops, this two, it represents the high current passes during the MOSFET on time. So when the switch on, this two dark gray loop is a high slew rate. So you want to make sure that this three loop on your PCB layout as tight as possible to make sure that the noises would not influence on your other components and influence on your whole circuit. So here's the PCB layout for the whole board. You see for the inner loop. So for the inner loop, it will through the RSNS here. So you want to make sure. Sorry for the like several high through rate loop. You could say like for this the input loop and also the output loop. You should make sure that the ground will be as close as to the components, as close as possible, because you want to make sure the loop is as tight as possible. And that's my favorite part of the Ultimate Designer. You can say your 3D model of your whole board. If you just stare at this PCB layout with different layers on just a plain board, you don't have any idea of how the components look like or how your board look like in the future. But with the 3D model here, you could easily tell like every component look like and every part of your circuit look like. Like this is our controller. It's very small right here, and our switching node here, the power MOSFET, the power diode, and the input and output capacitors, and the input of the circuit, output of the circuit. It's really clear, and you can have a clear idea of your board before you're soldering or something like that. I put several design ideas here, like which I think is really important for your design. The first one is in order to reduce the noise of the switch node here, you could say like the pin, all the pin with the switch sign here. You could say that this polygon here. You want to make sure that the switching point is like noises point on your board. So you should use the polygon to connect every switch point pins. And at the same time, we hope to avoid the switch influence on other pins, so the polygon would better not extra shapes. You see, it's not just a square shape here. I cut it off because you don't want extra shapes of your switching point to like annoy other pins. And for this part, according to the datasheet of LM5022, its current sense and the PWM comparators are very fast and may respond to short duration noise pause. So the capacitor associated with the CS filter must be placed very close to the device and connected directly to the pin of the controller. So you can say the RG here. I use RG to separate the CS filter and the switching point to reduce the noise. Maybe you couldn't tell like too much. It's not very away from each other, but for the board size, it's a little bit distance would mean a lot. So the RG will like build a space from switch node and the CS filter. And I also use polygons for the current sensing part here. And in order to minimize each ground loop, place the via as close as the component to the component as close as possible. So it can also help reduce the AC loop impedance. You can see via will be like this, the little via here. For the high power loop, you want to pick, you should put more vias between the ground. Yeah, this one is for the like Type 2 controller. This is how the real board look like. It's a female socket for a Type 2 controller. Use the female socket, the header connector, instead of the surface mount device soldering for Type 2 components, because just I mentioned, the actual power plant may be different. Not just the power plant, maybe the actual Type 2 and also the MOSFET or the diodes may be different from the simulation. So that female socket, the header connector, may be like more convenient for debugging for your circuit. And for the third part, it's a band soldering. Here's my bench for the soldering part. And I want to introduce several components I used here. The first one is the soldering iron, and all the components is in the like plastic box. You can collect them together. It's easy to find what you want. And this is the hot air soldering station, and this one is the solder paste stencil. This tool is really convenient when your board have several surface mount components. You could tell that a little hole on this. You could ask for this when you order your PCB board online. When you have several surface mount components, you could finish your soldering at once, like more convenient than use the soldering iron. So here's the comparison of the blank board and with the whole board. I have finished the soldering. The left one is the board you will get from the PCB website. That's what you'll get from the Orion website. And this is like after soldering, after I solder all of the components on the board. And you can see like different colors of the test point. You could easily figure out when you are testing. And for the ground pin, you could solder a line here to, you could touch, like, you could put several like a ground test pin here on the one ground. It's more convenient when you are testing. So the final part is the test results of the whole board. Here's like several photos when I'm doing the test. You can see like I use the carbon port. Well, I will show you later. Yeah, for the power supply is a switching mode power supply, which has the range 1 to 60 volts DC volts, and with 5 amps. And this one is the oscilloscope. And I also use the adjustable resistors as the load of the board. And this one is the current probe to test the input current or the output current. You can see the wave on the oscilloscope with the current probe. That's the PCB assembly and the bench setup. I must say it's really excited when you see the waveforms show on the oscilloscope. Of course, the waveform you want show on the oscilloscope, not the noises or something else. So the first test result will be the efficiency curve. I built the efficiency curve from 3 different input voltages. The first one is the 6 volts, and the second one is 25 volts, and the last one is 48 volts. you could say the efficiency curve over here. The maximum efficiency will be 90%. Here's a low transient response. When I test the undershoot and overshoot for each circumstance. When the input voltage equals to 6 volts, and the low transient from 50 milliamps to 100 milliamps, the undershoot will be equals to 266 millivolts, and the overshoot will be equals to 255 millivolts. It's not met. It's really close to the simulation result, the TINA-TI simulation result. The undershoot and overshoot is in the acceptable. Here's when the weighting equals to 25 volts. We could see that the undershoot and overshoot values become smaller when the input voltages become larger. And it got its minimum value when the input voltage equals to 48 volts. And here's the startup simulation. You can see the software start when the power supply turn on. Also, it shows under different circumstances with different input. And this is the shutdown test results with different input values, input voltages. You say it's clear to say that with different duty cycle, it has different shapes of waveforms. So for the output voltage ripple, we could use the AC coupled to test the output voltage ripple. The ripple of the output voltage becomes smaller and smaller when the input voltage got larger and larger. You can easily tell from the waveforms. And when the output voltage ripple is at its maximum is at when the Vin voltage equals to 6 volts, and the minimum while at the 48 volts. Input voltage equals to 48 volts. And this one is the discontinuous condition mode. You could do the several tests when you're finished your board to say, to realize when to do something with the simulation you have done when you start your design. It's really fun and really interesting. And I'm really excited to see your board work very well and work as you want. So this is the N-gate raise and fall time as the MOSFET I chose. So it's under different circumstances, the raise time and the fall time. I also do the overload test. So the output voltage drops significantly when the input voltage equals to 6 volts. We can see here the output voltage has only 37 volts, and it should be stable at 50 volts. But when the in overload test, it drops significantly. So other inputs also have different degrees of voltage drop, but can tell it's not very as much as when the input equals to 6 volts. And here's I checked the CS pin and the V voltage of the gate under different input voltage when the load increased. As the load increases, the voltage shape of the CS pin is closer to the sawtooth waveform. And when the load is light, the voltage of the CS pin has an obvious cutoff. I also put the RCD snubber in my appendix, but it's not on my real board. For the RCD snubber, it's a form of circuit protection against the voltage spikes, raining, and oscillation effects. It's generally used in flyback circuit because the copper inductor will produce leakage inductance. I didn't use in my boost converter because you can see from the test result, it could also work well without RCD snubber. And I don't really familiar how to design an RCD snubber because I'm not sure about the leakage inductance in my circuit. So I don't want to ruin the whole design because of the RCD snubber. So that's why I put it in my appendix. Yeah, for that's all of my design. I hope I make a clear explanation of the boost converter design, cover mode boost converter design. So if you have any questions, I'm willing to answer.
Before going to the question answer session, can I request you to say that the presentation can we host in a public domain, madam?
The what?
The presentation what you made for the benefit of other members, can we keep on our in our site?
Yeah, yes, of course.
Yeah. Thank you. Thank you very much. Thank you very much.
Yeah, of course. I appreciate it. Any questions?
We will send the link also to you where it is there. No issues. Any Dr. Aswin, you can ask other people to any questions are there. What I could see the talk is more technical, more and more technical to the people of the core technologies. Maybe some of the people may not reach that level. That's the reason that I requested Zhang that to permit to us to keep the presentation in the web so that people can see once or twice and they themselves will understand more depth and do some kind of a work in the direction. Therefore, that was one of the reasons that why I requested Zhang to permit to keep that. And she kindly agreed to that. Thank you for that. And if anybody has any questions, kindly.